Welcome to all in exam days. This is the electromagnetic induction and we are here for self and mutual inductance. First we will see what is the difference between the self and mutual inductance. What actually the mutual inductance is, how it occur and how the one inductance influence the other. That is what we will see in the mutual inductance. Also we will see the time relation of the mutual inductance and self inductance with current. We will see the problems that are based on inductance in this lecture. Self-inductance. Now for this, consider an single isolated circuit you can consider. In this circuit, like this, when current flows, any circuit you can consider, and in that circuit, when the current is present in the circuit, then that circuit produces the magnetic field. And if there is a change in magnetic field, then there is magnetic flux, or you can say if there is a magnetic field, obviously there is a magnetic flux, but that we already know that phi is equals to given by B dot A. Okay, so when the flux changes, with the time, then there is EMF introduced. Okay, so whenever there is a flux change, then EMF is generated. Now, what Faraday says regarding the self-inductance, that whenever there is any change in the flux in the circuit, it is produced by induced EMF. Now, important thing is, this is in a circuit. The flux is in a circuit. Okay, means the flux change itself in the circuit. Okay, and that is due to the induced EMF. Means you can say that produces the induced EMF. Okay, then that EMF is given some special name. That special name is what we call self-induced EMF. Now, what does this mean? So, as per the name, you can easily understand this is self-induced, because here the source of induction of EMF is the change of current in the same circuit. Okay, so if we talk about self-inductance, first thing is the self circuit, or you can say same circuit, in which current is flowing, isn't it? Second thing, there is induced EMF. Induced EMF due to same circuit. Induced EMF is due to change in flux. Okay, so these are the important points. So this is according to the Faraday. Now what Lenz talk about this? Lenz says that whenever the self-induced EMF is there, then always oppose the change in the current, and that change causes the EMF, and that tends to make the more difficult for variation of the current to occur. Okay, that is what we call self-inductance. Okay, self-inductance, which is denoted by sign L. So self-inductance in the circuit is always, we can say, have an importance regarding the you can say its flow of current. You will understand that how the self-inductance is important regarding this, especially when we talk about the flux. So if I define the self-inductance, I can say simply there are many definitions regarding the self-inductance. So what we can simply understand this, that suppose there is a circuit, okay, and that circuit is there, then circuit has n coils like this. Not n coil means n turns. So here turns are n, and in this coil the current is I. Then what is the flux in this current? Or you can simply say total flux. Okay, total flux is directly proportional to current. Okay, what does this mean? we can say that total flux is here N phi, and which is directly proportional to the current I. We can say here current is capital I. Okay, so total current is this one. Now when we remove proportionality sign, there is some introduction of some proportional constant, that is Li. Okay, so when L phi is equals to Li, it means what is your L? L is here N phi by I. Now understand this. What this L is called? This L is called self-inductance. So this proportionality sign that is removed and we introduce such constant that is L, and that depends upon the dimension of, you can say, depends upon dimension and number of turns of coil. Okay, so this constant is what we call self-inductance. This is constant. So total flux is what we call N phi, which is equals to Li. Okay, so total flux per unit current, simply we can say total flux per unit current is what we call self-inductance. Okay, so you can define this: total flux per unit current. Now this inductance, self-inductance has some unit, and that unit is simply Henry, which is denoted by capital H. Clear? This is the first basic thing regarding the inductance. Now if I say another thing, means if we discuss about the one more important thing, that we all know that if current pass through a circuit, then there is a magnetic field. Due to that magnetic field, there is flux, and whenever there is a flux change, what we can say, EMF is induced. Now if I simply talk about that, flux depend upon magnetic field depend upon I, EMF depend upon flux, actually rate of change of flux. So if I say the rate of change of flux means it depends upon dV over dt, it means it also depends upon di over dt. Simple. Means all in all, what I want to tell you is that whenever there is EMF, then it depends upon rate of change of current. Okay, so when a current, suppose a current I, you can say current I is passing through a circuit, okay, and that current is changing with a certain rate. So rate of change of current is what we can say di over dt, and we all know that EMF is induced in such situation, and EMF is directly proportional to di upon dt. Now when we remove this proportionality sign, so we have certain constant, that is L di over dt. Now one more important thing, what this negative, first thing is, what is L? L is your self-inductance. Okay, and what is minus sign indicate? Minus sign. So minus sign is here due to reflection of Lenz law. Okay, reflection of Lenz's law. What does this say? It says that the self-induced EMF in the circuit always oppose any change in the circuit, any change of current in the circuit. From here, what I can say, that inductance will be, self-inductance will be given by mod of EMF over di by dt, rate of change of current. That is what self-inductance is. So self-inductance in any circuit is magnitude of what? EMF per unit rate of change of current. Okay, EMF per unit rate of change of current is self-inductance.